When's the last time that you had to replace something that was pretty expensive? If you've ever had to retire your car, it might have been because it was getting old, the mileage wasn't as good, you have to take it into the shop pretty frequently, or maybe it's just not reliable anymore in getting you from point A to point B safely. If you've ever gotten a new cell phone because the operating system isn't going to be upgraded anymore or security updates won't be pushed to it, then this would be an example where the requirements for having a secure phone have changed and your old phone just isn't compatible anymore. Or if maybe you had an HD TV and then as soon as 4K came along, suddenly HD just doesn't cut it. That would be an example where technology changes from generation to generation, and even though what you had before still operates in the same way, it's just not as attractive as what's available now. Those are all examples of real-world consumer decisions about replacement that have analogs in the engineering world. If we're thinking about factory equipment and replacing that as it gets older, then we need to know how the economics work out. For all of Chapter 9, what we're going to do is refer to an asset that's currently in place as a defender, and the proposed replacement is going to be the challenger. This video will walk through the conceptual underpinnings of how we think about replacement analysis using a fairly simple example, and then we'll start thinking about the useful lifetime of a project as being a variable. We always thought of it as being constant before, but now we want to think of it as variable and understand how to do an analysis that allows us to calculate how long we should operate an asset if we're thinking from an optimal economic standpoint. There are a few types of questions that we ask in replacement analysis. The first is a situation where the challenger is technologically superior to the defender. It produces more benefits. Maybe it's higher quality, maybe it's faster. We don't know, but it's better. If that's the case, we want to know what it would take to upgrade the defender in order to put it on an even footing in terms of the amount of benefit that it provides. In the other situation, the defender and the challenger might be equal to each other in terms of the benefits they provide, but the defender is getting older, the operations and maintenance costs are going up, and so we want to know at what point is replacement of the defender by a challenger justified because it's going to reduce our annual expenses. I've said before that we keep seeing the same types of problems again and again throughout the semester, and this is no exception. Replacement analysis is really very similar to the types of problems that we've already been doing. It's just a little bit more nuanced. And so we just have to ask ourselves what's different between this situation and the kind of problems that we already know how to deal with. If we're in a situation where we want to know whether or not to replace a defender with a challenger at a specific point in time, then our approach is pretty much identical to what we've done before. We just compare the economic value associated with the challenger with whatever the remaining value is associated with keeping the defender in service. So if that's the case, the only difference is that one project is midway through its useful life already. On the other hand, if the question is when should we replace the defender in the future, then our approach now is to calculate its worth as a function of its useful lifetime. Previously, we had always said that the lifetime of a project was a fixed value, but now we just want to allow that to vary and see how the worth changes as a function of how long we keep using something. If we're talking about a well-maintained piece of equipment, in practice, a lot of the time you could keep it operating almost indefinitely as long as you spend enough to maintain it or to replace individual parts when they break down. So the question is, what governs the lifetime of an asset in practice? If it's going to get more and more expensive to maintain the equipment, at what point do we say enough is enough? We just have to replace everything. Well, the answer is economics. You guessed it. That's why we're talking about it in this class. So, a couple of clicker questions for you out in YouTube watching land. The market value and annual expenses associated with an asset are likely to change over time by the market value going up or down and the annual expenses going up or down. Think about it. Click in your answer. Yeah? Make sure you get credit for it. All right. Yes, so the market value goes down over time. The annual expenses generally go up. Next question. The equivalent annual worth of an initial investment is going to go up, down, or to the moon if we extend the lifetime of the project. It's going to go down, right? We extend the lifetime, and so the annual worth is extended over a longer number of years. So the annual worth is going to generally go down. In that case, we have a trade-off when we put those two facts together. If we add another year to the lifetime of an asset by continuing to operate it, some costs go down and others go up. So a company is going to choose the amount of time that they use an asset by estimating the length of time that minimizes what's called the expected uniform annual cost. This is called also the economic lifetime. So this concept is often what's used to actually set the planning horizon for an analysis. A company will calculate what's the economic lifetime of an asset, and they'll use that for your planning horizon. So what this means is that we want to calculate the expected uniform annual cost as a function of the asset lifetime, and the one that minimizes it is the economic lifetime, and that's how long we plan to use the asset. In the next video, we'll work through the mechanics of that, but first we're going to do a simple example. Take a moment, pause the video, and read the question. Did you pause it? Are you reading it? Okay, so first off, I'm going to ask one question. What information is missing? Aha! You might say to yourself, you never told me the hurdle rate that Duke Energy uses. And I would say, that's exactly right. That's what's missing. So first, to make it simple, we're just going to use a hurdle rate of 0%. All the information in the problem is laid out in this table here. And I want to point out that this is a simple version of replacement analysis. We have a constant study period of 5 years. We know that the boiler has to be retired at that point no matter what. And our choice is just, do we replace the Defender now or in 5 years? We're not asking when in this 5-year period should we replace it. The next thing I'm going to point out is in this table, we're using the current market value of the Defender, not the current book value and not the initial investment. The initial investment back in 1972 is a sunk cost at this point. And so we're thinking about the market value as an opportunity cost associated with keeping the Defender. So we're assigning that like it's an initial investment, even though it's not. Okay, it's what we could sell the Defender for today. And if we don't sell it, then we're giving up the opportunity to have that $300,000. On the other hand, once we're looking at the value of the Challenger, we are not going to double count by also including the market value of the Defender as a discount to the cost of the Challenger. The cost for the Challenger, the new boiler, is $1.2 million, not $900,000. It's true that if we go with the Challenger, we would sell the Defender today and get that $300,000. But if we included it as both like an initial investment in the Defender and a discount in the Challenger, it's double counting by assigning that value to both of the assets. So we're not going to do that. If we want to calculate the present worth of the Defender and the Challenger and compare them to get our answer, we're going to take the market value of the Defender today, subtract the market value at the end of the study, and then add in 5 years of annual O&M costs of $600,000 per year. For the Challenger, we have the initial investment today of 1.2 million. The market value at the end is 500,000, so we can subtract that off, and we've got 5 years of O&M costs of $300,000 per year. Because the hurdle rate for this simple example is 0%, we don't have to do any sort of conversion. We can just add and subtract those numbers. And that gives us a present worth of the Defender of $3.2 million in cost, so it's negative, and the Challenger has a worth of $2.2 million in costs. Therefore, we would take the Challenger because it's the least cost alternative. In the next video, we'll relax the assumption of having a constant useful lifetime or planning horizon and learn how to calculate the economic lifetime. See you then.